Okay, well, we've been working on this rational number arithmetic system, and then what we did, right, the important thing about what we did is we thought about the problem by breaking it into two pieces. Right, we said, assume there's this contract with George, and George has figured out the way to how to construct these clouds, provided us procedures make-rat, which was a constructor, and selectors, which are numerator and denominator, and then in terms of that we went off and implemented addition and multiplication of rational numbers. Well, now let's go look at George's problem. Right, how can we go and package together a numerator and a denominator to actually make one of these clouds? See, what we need is a kind of glue a glue for data objects that allows us to put things together. And Lisp provides such a glue. And that glue is called list structure. List structure is a way of gluing things together. And more precisely, Lisp provides a way of constructing things called pairs. Okay. There's a primitive operator in Lisp called const. We can take a look at it. There's a thing called const. Right. Const is an operator which takes in two arguments called x and y, and it returns for us a thing called a pair. Right? It's a thing called a pair, right, that has a first part and a second part. Right? So const takes two objects. There's a thing called a pair. The first part of the const is x, and the second part of the const is y, and that's what it builds. And then we also assume we have ways of getting things out. If you're given a pair, there's a thing called car, and car of a pair P gives you out the first part of the pair P, and there's a thing called cdr. The cdr of the pair P gives you the second part of the pair P. Okay, so that's how we construct things. There's also a conventional way of drawing pictures of these things, just like we write down, just as we write down that as the conventional way of writing Plato's idea of 2. The way we could draw a diagram to represent consts of 2 and 3 is like this. We draw a little box, and so here's the box we're talking about, and this box has two arrows coming out of it. Let's say the first part of this pair is 2, and the second part of this pair is 3. And this notation has a name. It's called box. It's called box and pointer notation. Okay. By the way, let me say right now that a lot of people get confused that there's some significance to the geometric way I drew these pointers, the directions. Like some people think it would be different if I took this pointer and turned it up here and put the 3 out here. That has no significance, right? It's merely you have a bunch of arrows, these pointers, right? And the boxes, and the only issue is how they're connected, not the geometric arrangement of whether I write the pointer across or up or down. Now it's completely unobvious, probably, why that's called list structure. We're not actually going to talk about that today. We'll see that next time. Okay, so those are pairs. There's const that constructs them. And what I'm going to know about const and car and cdr is precisely that if I have any x and y, right, if I'm going to say if I have any things x and y, and I use const to construct a pair, then the car of that pair is going to be x, the thing I put in, and the cdr of that pair is going to be y. Right, and that's the behavior of these operators, const, car, and cdr. Given them, it's pretty clear how George can go off and construct his rational numbers. After all he has to do, remember George's problem was to implement make-rat, numerator, and denom. So all George has to do is say define make-rat of some n and a g, well, all I have to do is const them. That's const of n to d. And then if I want to get the numerator out, I can say define the numerator, numer, of some rational number x. If the rational number is implemented as a pair, then all I have to do is get out the car of x. And then similarly, define the denom is going to be the coulter, the other thing I put into the pair. Okay. Well, now we're in business, right? That's a complete implementation of rational numbers. Let's use it. Suppose I want to say, so I want to think about how to add 1/2 plus 1/4 and see, watch the system work. Well, the way I'd use that is I'd say, well, maybe define A, I have to make a 1/2. Well, that's a rational number with numerator 1 and denominator 2. So A will be make-rat of 1 and 2. And then I'll construct the 1/4. I'll say define B to be make-rat of 1 and 4. And if I'd like to look at the answer, well, assuming I don't have a special thing that prints rational numbers, or I could make one, I could say, for instance, define the answer to be plus rat of A and B. And now I can say, what's the answer? What are the numerators and denominators of the answer? So if I'm adding 1/2 and 1/4, I'll say, what is the numerator of the answer? And the system is going to type out, well, 6. Bad news. And if I say, what's the denominator of the answer? The system's going to type out 8. So instead of what I would really like, which is for it to say that 1/2 and 1/4 is 3/4, this foolish machine is going to say, no, it's 6/8. No, that's sort of bad news. Where's the bug? Why does it do that, after all? Well, it's the way that we just had plus rat. Plus rat just took the, right, it said you add the numerator times the denominator. You add that to the numerator times the denominator and put that over the product of the two denominators, and that's why you get 6/8. So what was wrong with our implementation of plus rat? What's wrong with that rational number arithmetic stuff that we did before the break? Well, the answer is, one way to look at it is absolutely nothing's wrong with it. It's perfectly good implementation. Follows the 6th grade, 5th grade mathematics for adding fractions. One thing we can say is, well, that's George's problem. Right? Boy, wasn't George dumb to say that he can make a rational number simply by sticking together the numerator and denominator? Right? Wouldn't it be better for George, when he made a rational number, to reduce the stuff to lowest terms? And what I mean is, wouldn't it be better for George, instead of using this version of make-rat, to use this one on the slide, or instead of just saying const together n and d, what you do is compute the greatest common divisor of n and d, and GCD is a procedure which, well, for all we care, is a primitive, which computes the greatest common divisor of two numbers. So the way I can construct a rational number is get the greatest common divisor of the two numbers, and I'm going to call that g, And then instead of consting together n and d, I'll divide them through. I'll const together the quotient of n by the GCD and the quotient of d by the GCD. And that'll reduce a rational number to lowest terms so that when I do this addition, when plusrat calls makerat, remember the definition of plusrat, it had a makerat in there, just by the fact that it's constructing that, the thing will get reduced to lowest terms automatically. Okay, that is a complete system, right, for rational number arithmetic. Let's look at what we've done. Right, we said we want to build rational number arithmetic. And we had a thing called plusrat. We implemented that. And I showed you multiplying rational numbers. And although I didn't put them up there, presumably we'd like to have something that subtracts rational numbers. And I don't know, all sorts of things. Things that test equality and division, and maybe things that print rational numbers in some particular way. And we implemented those in terms of pairs. These pairs, const, car, and coulter, that are built into Lisp. But the important thing is that between these and these, we set up an abstraction barrier. We set up a layer of abstraction and what was that layer of abstraction? That layer of abstraction was precisely the constructor and the selectors. This layer was makerat and numer and denom. This methodology, right, another way to say what it's doing is that we are separating the way something is used, separating the use of data objects from the representation of data objects. Right, so up here we have the way that rational numbers are used, do arithmetic on them. Down here we have the way that they're represented, and they're separated by this boundary. The boundary is the constructors and selectors. Okay. And this methodology has a name. This is called data abstraction. Okay. Data abstraction is sort of the programming methodology of setting up data objects by postulating constructors and selectors to isolate use from representation. Well, so what? I mean, after all, we didn't have to do it this way. It's perfectly possible to do rational number addition without having any compound data objects. And here on this slide is one example. See, we certainly could have defined plusrat, which takes in things x and y, and we'll say, well, what are these rational numbers really? Right? We'll say, well, really they're just pairs, and the numerator is the car and the denominator is the coulter. So what we'll do is we'll take the car of x times the coulter of y, multiply them, take the car of y times the coulter of x, multiply them, add them, take the coulter of x and the coulter of y, multiply them, and then constitute together. And that sort of does the same thing. Right? But this ignores the problem of reducing things to lowest terms, but let's not worry about that for a minute. Well, so what? Why don't we do it that way? Right? After all, there's sort of fewer procedures to define, and it's a lot more straightforward. Saves all this self-righteous BS about talking about data abstraction. We just sort of do it. I mean, who knows? Maybe it's even marginally more efficient, depending on whatever compiler we're using for this. Right? What's the point of isolating the use from the representation? Well, it goes back to this notion of naming. Remember, one of the most important principles in programming is the same as one of the most important principles in sorcery. Right? That if you have the name of a spirit, you get control over it. And if you go back and look at this slide, you see what's in there is we have this thing plus rat, but nowhere in this system, if I have a plus rat and a minus rat and a star rat and things that look like that, nowhere in this system do I have a thing that I can point at, which is a rational number. Right? I don't have in a system like that the idea of rational number as a conceptual entity. Well, what's the advantage of that? What's the advantage of isolating the idea of rational number as a conceptual entity and really naming it with make-rat, numerator, and denominator? Well, one advantage is you might want to have alternative representations. See, before I showed you that one way George could solve this things not reduced to lower terms problem is when you build a rational number, you divide out by the greatest common denominator. Another way to do that is shown over here. I can have an alternative representation for rational numbers where when you make a rational number, you just const them. However, when you go to select out the numerator, at that point, you compute the GCD of the stuff that's sitting in that pair and divide out by the GCD. Right? And similarly, when I get the denominator, at that point, when I go to get the denominator, I'll divide out by the GCD. So the difference would be in the old representation, when ants was constructed here, say with 6 and 8, in the first way, the 6 and 8 would have got reduced when they got stuck into that pair, and numerator would select out 3. And in the way I just showed you, well, ants would get 6 and 8 put in, and then at the point where I said numerator, some computation would get done to put out 3 instead of 6. So those are two different ways I might do it. Which one's better? Well, it depends, right? If I'm making a system where I am mostly constructing rational numbers and hardly ever looking at them, then it's probably better not to do that GCD computation when I construct them. If I'm doing a system where I look at things a lot more than I construct them, then it's probably better to do the work when I construct them. So there's a choice there. But the real issue is that you might not be able to decide. At the moment you're worrying about these rational numbers, see, in general, as systems designers, you're forced with the necessity to make decisions about how you're going to do things. And in general, the way you'd like to retain flexibility is to never make up your mind about anything until you're forced to do it. And the problem is there's a very, very narrow line between deferring decisions and outright procrastination. So you'd like to make progress. You'd like to make progress, but also at the same time never be bound by the consequences of your decisions. Data abstraction is one way of doing this. What we did is we used wishful thinking. See, we gave a name to the decision. We said make-rat, numerator, and denominator will stand for however it's going to be done, and however it's going to be done, it's George's problem. But really what that was doing is giving a name to the decision of how we're going to do it, and then continuing as if we'd made the decision. And then eventually, when we really wanted it to work, coming back and facing what we really had to do. And in fact, we'll see a couple of times from now that you may never have to choose any particular representation, ever, ever. Anyway, that's a very powerful design technique. It's the key to the reason people use data abstraction. And we're going to see that idea again and again. Let's stop for questions.
What does this delaying decision-making through abstraction layers do to the maxim of do all your design before any of your code?
Well, that's someone's axiom, and I bet that's the axiom of someone who hasn't implemented very large computer systems very much. I said that computer science is a lot like magic, and it's sort of good that it's like magic. There's a bad part of computer science that's a lot like religion. But in general, I think people who really believe that you design everything before you implement it basically are people who haven't designed very many things. The real power is that you can pretend that you've made the decision, and then later on figure out which one is right, which decision you ought to have made. And when you can do that, you have the best of both worlds.
Can you explain the difference between let and define?
Oh, okay. Let is a way to establish local names. Okay. So let me give you sort of a half answer, and I'll say maybe later on we can talk about the whole very complicated thing. But the big difference for now is that, see, when you're typing at Lisp, you're typing in this environment where you're making definitions. And when you say define A to be 5, if I say define A to be 5, then from then on the thing will remember that A is 5. Okay? Let is a way to set up a local context where there's a definition. So if I type something like saying let A, no, I shouldn't say A. If I said let Z be 10, and within that context tell me what the sum of Z and Z is. So if I typed in this expression to Lisp, and then this would put out 20. However, then if I said what's Z, the computer would say that's an unbound variable. So let is a way of setting up a context where you can make definitions. But those definitions are local to this context. And of course, if I'd said A in here, I'd still get 20, but this A would not interfere at all with this one. So if I type this and then type this and then say what's A will still be 5. So there's some other subtle differences between let and define, but that's the most important one.